Alright, so here's a topic that we are going to cover in much more thorough detail later, but let's talk about reflection and refraction in its basic form here. Suppose two observers are looking at the same object on either side of this window. Suppose the object is on the same side as observer 2, so observer 2 sees the reflection of the object, while observer 1 sees the object directly through the window. Light is radiating away from the object at all angles and at all points of the object. But what's shown here is just one ray that makes it exactly to both observers. So just to simplify the image, we usually take away all of the other rays that are emanating in all the other directions and just focus on the principal rays that are important to demonstrate what's going on. It travels from the object to the glass, where a portion of the light is reflected and the rest refracts through the glass. Observer 2 sees the image of the object straight through the glass. This is because light does not carry an encoded history of its journey as it enters our eyes, so our brain makes the best assumption it can, that this light must have been traveling in the same direction since always. Oftentimes, however, this assumption is not correct, and the light has reflected off of a highly reflective surface, reflective enough to form a clear false image and trick our brain. Reflection, it turns out, can occur for both smooth and rough surfaces. If the surface is rough, we call it diffuse reflection. If the surface is smooth, like glass, we call it specular reflection. Almost everything you see is visible to you because it is reflecting light from the sun, a light bulb, or some other source diffusely off the object and to your eyes. But for the purposes of our study of optics, since we're concerned with the images that are formed from reflection and refraction, we'll assume all the surfaces are smooth and thus demonstrate specular reflection. So regarding both reflection and refraction, the following statements can be made. The first statement is that the incident, reflected, and refracted rays and the normal to the surface all lie in the same plane. So if we have a region here, which is, we'll say, material 1, and we have another material here, right, side by side, and we have some rays here. If we have, let me do this first. The normal to the surface is something like this, right? So if we have a ray approaching like this, and it hits that interface right there, it makes an angle theta sub I for incident, I for incident. And if we're looking at reflection, the angle of reflection equals the angle of incidence, such that this is also theta. I'll label it exactly the same, since it's exactly the same angle. If we're looking at the portion of this ray that refracts through the interface, then it follows a law that we are going to identify in a short bit. And it refracts at a different angle. I'm going to say theta sub r. So I'll read the statement again while you look at this image here of the reflected and refracted ray. The incident, reflected, refracted rays, and the normal to the surface all lie in the same plane. Right, so nothing's coming into or going out of the page. They're all in the same plane of this page of your screen. All right, so that's statement 1. Statement 2 is something that we kind of mentioned within statement 1, that the angle of the reflected light is equal to the angle of the incident light. So I for incident equals theta I, theta reflected. And that would just be these guys here. When light travels through the material, it travels slower than it does in a vacuum. And this is largely because there is stuff in the way for it to get through. And I'll caution you again on simplifications. Light travels slower through some materials than others, according to the properties of the material. Because of this, when light crosses a boundary between two materials, it changes speed. Let's look at the wavefront visualization to see what happens. So if we have this interface here, talking about refraction, and we have wavefronts approaching, right? So we're going from rays back over to wavefronts, and we'll say this is material 1 over here, and this is material 2 over here. Same up there. And we look at wavefronts approaching, and we're modeling this same kind of picture here, but with wavefronts. Then we have wavefronts approaching kind of like this. And what happens is it bends at that point, right? So why does that happen exactly? Well, let's go even closer to that interface here. So same exact situation, we're just going to zoom way in to like maybe this big. So now we are approaching. On the left is material 1, on the right is material 2, and we're approaching. We have these wavefronts here. Those other ones shouldn't have been shorter. All right, so one way to picture why this happens, so you can see mid-wavefront, it kind of bends right at that interface. So within one single wavefront, you have kind of a bending. And one reason, one way to picture why this happens is to imagine if you were to hold out your arms, or maybe to exaggerate it, if you were to link arms with 10 or 15 people side by side, and you were the wavefront, you and all of the people that you're linking arms with. And then you imagine a line of tape on the ground several paces in front of you, and you were to approach this piece of tape at an angle. So your wavefront is approaching the tape like an angle, just like this drawing. So if you have the person who hits the interface first, so if this is, a bunch of people, and when they hit the interface, if they're instructed to slow down, so go from like a faster pace to slower pace, right when they cross that interface, then what you will find is the entire wave will end up bending, because this is going at some speed, but now it's going at some smaller speed here. I don't know if you can picture that in your head, but that to me really sends it home when I think about discrete parts of the line slowing down little by little, and it kind of just warps the wavefront and it bends it. You can also find videos of this online if you can't imagine it in your head. There's lots of different videos that demonstrate it, and you may even be able to find one where people are linking arms like that. Anyways, that's why refraction happens, is because it's a change of speed, and you have to imagine the wavefronts changing speed at exactly the interface. And so as that change of speed propagates across from one end of the wavefront to the other, it causes a warping and a change in direction of that wavefront. The speed of light travels through a material. The speed that light travels through a material is given by the index of refraction, or the refractive index, same thing, denoted by the letter n. This quantity is just the ratio of the speed of light in the material and the speed of light in a vacuum. So it's literally speed of light in a vacuum c over the speed of light in whatever material you're talking about. It's a ratio of speeds, and so therefore it's a unitless number. So since the speed of light through a material is always slower than the speed of light through a vacuum, this number will always be greater than 1. Always be greater than 1. With this quantity, we can now present the law of refraction, which is what I was hinting at when I said we will show later what determines this angle right here. So we have a law called Snell's law, but there's, I'll say, some debate over whether Snell actually discovered it. So we'll call it the law of refraction, whereby you have the index of refraction of material 1 times sine of the angle that the light approaches, and that angle is relative to the normal. That is equal to the index of refraction of material 2 times sine of the angle that it refracts at, this angle. It's quite simple and pleasing little law. It explains why when you look at your straw in a glass of water, the straw is bent. It explains why light refracts. So in words, this equation says, statement 3. Given two materials, material 1 and material 2, with respective indices of refraction, N1 and N2, light incident at the boundary between the two materials, approaching at angle theta 1 from the normal, will refract at an angle theta 2, also from the normal. And that is exactly what is demonstrated in this drawing here. Notice that the path of light is reversible, meaning that it would take the same path regardless of which direction it's traveling. So you can take a moment and make up some angles and use some common indices of refraction and figure out what it would be if the light were instead traveling this way. And you would find that it travels the same exact path. So if this was your angle of incidence, then that would be your angle of refraction. It's easily verifiable. So given the right combination of refractive indices and incident angle, there's this interesting thing that happens. It's a phenomenon called total internal refraction. And for this to occur, the following condition must be met. So that's it for the big giant statements. This is just an interesting tidbit here. This condition, sine crit for critical, is equal to N2 over N1. So this is the angle of incidence that it approaches some surface. So what we're saying is if it approaches at a certain angle, then light does not leave the material. It doesn't refract. It actually refracts back inside the material. It's kind of bizarre. And it acts as if it's reflecting off the surface, but it's just refracting so much. So let's see. So if you were approaching like this at this angle, then it would refract some amount. And if you approached at this angle, an even bigger angle, hopefully this isn't too much of a mess, then it would bend even more. And you approach at a bigger angle, right, this angle, then it would refract even more. And if you get to a certain angle, this really, really large angle with a normal, then at some point, these continue to go inwards, and you are reflecting, or refracting, I guess, technically, back inside the material. So this is the same material. It's a very, very interesting phenomenon, and that's how fiber optics work. So that's how light is captured inside of a glass tube. And one more thing before we move on. I want to bring up one interesting and subtle consequence of waves changing speed through materials. Considering the wave aspect of light, when light slows down as it crosses from one material to another, its frequency mustn't change. If it did, this would be a creation or destruction of energy, and thus violate conservation of energy. So its frequency does not change. However, its wavelength must change because of this, because of the wave scrunching up as faster and faster traveling wave fronts run up on the slower traveling wave fronts at the interface, right? So if these are constantly slowing down, then these are constantly running up on them. And so this scrunching up, remember, these track with the wavelengths. So the frequency doesn't change, but the wavelength does change when it refracts. And so therefore, in a laboratory or theoretical setting, such as my lab actually, where energy is a concern and light is refracting through materials commonly, it's common to talk in terms of the frequency of light, which is unchanging, instead of the wavelength, which may be changing a small amount constantly. So that's just a subtle, interesting tidbit.